Lesson 112 now. We're going to start, it's over transformation. So our learning goal for today is that we can construct a function that is an additive or multiplicative transformation of another function. And here's what I want you to know. When it says additive, that means you can add or subtract. It's not necessarily one or the other. You could add or subtract. It doesn't have to be positive numbers. And the same thing here, when it says multiplicative, that could be multiply or division. So we're going to look at transformations today. The type of transformations we're not going to do is we're not going to do rotations, and we're not going to do absolute values. But you probably don't, maybe you remember from geometry what a rotation is, but we're not going to do those today, but we are going to do additive and multiplicative transformations. So when we look at these, what I want you to know before we get started is about the parent function. A parent function is the most simple function, or you could say simplest, most simple function of a family of functions. Family of functions, linear, quadratic, cubic, square root, etc., share similar algebraic properties, graphs, and behavior. What I'm about to do is rattle off, I don't know, something like 10 different parent functions here. We'll just make quick notes on them and we'll move on. So this part of the packet, we're going to be flying through here. So the first one is a constant function here. This is a constant function. C is a constant. I want you to write that in. C is a constant, which means it's not a number that's changing. So in this particular problem, this graph would actually be f of x equals, what is that, 3.5? Because the y value does not change. It looks like it's 3.5 for the entire graph. So that would be a constant function. The next one is a linear function. A linear function is this is the parent function for y equals mx plus b. That's just y equals x. Notice there. They call it identity. We might often call it a linear. Let's put that note there. That's a linear function. The next, y equals x squared. They call it quadratic. What's the name of the shape? What do we call it? Parabola. Just put the name parabola on the side. That's the name of the shape. And finally, the last for this grouping is the cubic function. The cubic function. And what do we call this shape? S curve. So go ahead and put on S curve there into your notes. This is what we call a linear or polynomial parent function set, meaning polynomials are whenever all the powers in the equations are whole numbers, and they are, which whole numbers means greater than or equal to 0. A constant is like an x to the power of 0. So this section, all the powers, there were no decimals, no fractions, nothing negative. They were whole numbers. That means 0, 1, 2, 3, 4, those type numbers. That's this first set of values. Okay. You don't need to know all that, but those are the parent functions you do need to know. These are all graphs without transformations. They haven't been shifted, reflected, stretched, shrunk, anything like that. Okay, next, going into the square root function here. This is a square root function. It looks, what it is it's half of a sideways parabola. Now, what do I mean by half of a sideways parabola? This isn't a part of the graph, but I'm going to add something here. If it went like this, you see how now it looks like a sideways parabola? Now, a square root, though, doesn't have the whole thing. A square root will only supply half the graph. So that's actually what it should look like. But I just wanted you to see what I mean when I say half of a sideways parabola. So it's missing the bottom half to make a parabola. The reciprocal, one thing mathematically I want you to write. If you have a root, what that means by power is that you're dividing by a power. So this would be the power of 1/2. A square root cancels a square because it's dividing by the power of 2. So put that this is equal to x to the 1/2 power. Notice I'm no longer polynomial. Remember how I said polynomials are 0 or whole numbers on the previous slide? Everything here was either a 0 power or a positive whole number power. So power 1, power 2, power 3, no power at all. Now I moved on, and now I got a fraction power. Now, reciprocal is the same thing as having a negative power. This is the power of -1. They call it reciprocal. We might call it rational. So write that down. And as far as the shape goes, I oftentimes call these C-curves. A rational function almost always, not always, but almost always has asymptotes because you're not allowed to divide by 0. So wherever your denominator would equal 0, you would have an asymptote or a whole. Okay, moving on. Absolute value function. What do I want you to know about this? This has to do with distance. So in math, we have to have a way to represent distance. Absolute value is how we do it. This, I would say V curve, but does it curve at all? No. So you could call it V lines. I'm just going to call it V graph. It's a V, or maybe I should say V-shaped. Let's just say V-shaped. The reason is when you talk about distance, we never deal with negatives. So I used to live around the corner. I'd walk to school every day for 5 years that I taught here. And when I walked to school, it was about a mile, just less than a mile. So when I walk home, do you think it would be negative a mile? No, why not? It's distance. Distance is always positive. It doesn't matter if you're moving left, right, up, or down. We say distance is always positive. So how do you represent that in math? You do it with absolute value. So whether you plug in a -x or a positive x, you get the same positive y value. Okay, and there's some examples right there. So that's how you do distance in math. Moving on, exponential. This is what Unit 2, the big portion of Unit 2 that we're finishing up Unit 1. AP Pre-Cal has 4 different units. We're about to complete Unit 1. Unit 2, a big portion of it is exponential and logarithms. There are 2 major graphs. Here's exponential growth and exponential decay. These we'll learn just for the sake of notes. These have horizontal asymptotes. The parent function would have a horizontal asymptote at y equals 0. Remember, asymptote just means a line or a curve that a graph approaches over time. It's going to approach that line y equals 0. This is growth as the graph takes off. This is decay. A lot of students think of these as like an airplane taking off the runway or an airplane coming to land on the runway. That's what exponential is. Extremely important, by the way, side note, for your life, if you want to be financially as free as possible. We all come into this world, different environment, different circumstances. Some are born to a rich family, some are born to a poor family. Some of you are born without a family. Some are born into a massive family. We all come into the world different situations. In the United States of America, though, if you want to enjoy as much financial freedom as possible from a mathematical standpoint, it'll be because obviously you can get lucky, but if you want to understand from a mathematical, it's because you understand how exponential functions work. So how many of you someday plan to buy a house? Your loan's going to be based off an exponential equation. How many want to buy a car? Again, unless you're going to buy for it up front, it might say $20,000 on the windshield. But if you take out a loan, you're going to be paying it off, and you're not actually paying $20,000. You're going to be paying more than that because it's going to be based off an exponential function. How many of you someday would like to own a company? So I got a couple hands up. I am a teacher. I don't actually own a company, but I own portions of companies. I own some of Apple, some of Microsoft, some of Ford, some of Honda, some of a bunch of different things through the stock market. Those are based off exponential functions. So honestly, if you want to know how do I enjoy as much financial freedom that's within my control, can't control who I was born to, where I was born, how big of a family I was born into, whether I was born in a family. You can't control all those factors, but what you can control is understanding exponential functions. That might help you have more financial freedom. So we're going to spend a lot of time on this, and I like it because it's very practical. All of you might not go into careers that use x cubes, x to the 4th power. You might not do that. But each of you, if you want to buy a house, want to buy a car, you're going to run into an exponential equation. The more understanding of that you have, the more you can take advantage of the math rather than someone taking advantage of you. Anyways, that was a little divergent. Okay, next one, logarithmic. This is the inverse of an exponential. So this, along with exponential, is what Unit 2 is going to be, for the most part, about. This will have a vertical asymptote. Because they are the inverse, of exponential, it's not going to be y equals 0. It's now going to become x equals 0. As y'all remember, inverse means switch your x and y. This is logarithmic growth, logarithmic decay. And again, to hit a few more here. Moving on to trigonometry. This is unit 3 now. Unit 3, though there are 6 trigonometric functions, I'm just going to list 3 on here. This is the sine. What do you think they call this shape? A wave. There you go. This is the sine wave. This is the cosine wave. Those are waves. And finally, there's sine, there's cosine, there is tangent. Tangent's next. This is the tangent, and these are S-curves. Whole bunch of S-curves repeating. That is what we're going to spend a lot of time of unit 3 talking about. Sine, cosine, tangent. I think I have one more, if I'm not mistaken. You all have the packet, you can look. I think I have one more set here that we'll see throughout the year. This one, what does this look like? Looks like steps. This is, some people call it a step function. The true name is the greatest integer. A lot of people call it step function, if you want to write that down. What is this in the real world? This is rounding. If you ever wonder, how do you apply rounding in mathematics? I mean, y'all know how to do it. But if you're just wondering, this is what this function is. So let's just say you go to the store, you don't have any money, you're with your parents, and you see something you want, and it's $9.85. Are you going to say, hey, Mom, Dad, can I have $9.85? No. No, what are you going to ask for? $10. Now, some of you are smarter than that, and you don't ask for 10. You first ask for 9, and then when you go up to pay, you're like, well, actually, it's about 10, because you'll round down first. But either way, that's what you do. We round. That's what this looks like. This is rounding. Notice there's nothing in between the whole numbers. That's rounding. Got all those? All right. Today, what we're going to do is take those graphs and we're going to transform them. Now, there are some transformations we're going to look at. The first one is reflection. So this now is transformations. That's what this line is. We're now moving into transformations. So what type of transformations might you see? The first one is a reflection. You can reflect. Now, reflections are the easiest to get right mathematically, and oftentimes on a multiple choice test, the easiest to get incorrect. I'm going to say that again. Mathematically, on your homework, it's going to be the easiest to get right. But on the test, it's very easy to get wrong because of something very simple here. This negative, you're going to hear me talk about, is it on the inside, is it on the outside? A lot. This negative is on the outside of the x is inside the parentheses. This negative is on the outside. What this would mean is you would reflect the y value. So let's go over here to your notes. Draw a dot right in that point. And I'm just going to pretend like that's 4 units to the right. 1, 2, 3, 4. We're going to say that's 4 units to the right, and I'm going to say that's 2 units up. That point is 4, 2. If you have a negative on the outside of the equation, it will reflect your y values, which means a positive 2 of a y becomes a negative 2. So the 4 stays positive, but the 2 becomes negative. Now, y'all are going to get that on the homework right almost every single time. That one's going to be easy for you. Then comes a test, and you're going to forget this. If you reflect your y's, they're going to ask you, which axis does it cross over, or is it reflected in? And most people are saying, well, I reflected the y, so I reflected in the y-axis. Not true. Which axis do we actually cross over? So you see how you cross over the x? That's the note that I want to put on here, tricky. Why is that tricky? If I'm reflecting y's, which axis do I cross over? The x. If you reflect your y's, you cross over the x. I'm going to be repeating that throughout the year a bunch of times because a lot of students miss that. So easy to do the math. Tricky on a multiple choice test that you just forget that. Okay, let's add the points here. Let's just say the point is right there. I'm going to say that's maybe about 3. 1, 2, 3. And then 1, 2. This time, notice where the negative is located. Where's the negative located this time? Next to the x on the inside. So that would mean if it's next to the x, you reflect your x's. So instead of being at 3, 2, it becomes negative 3, 2. So we got that point over here. Now, if you reflect your x's, which axis do you actually cross over?
Y.
We cross over our y-axis. So again, that's the tricky part. So if you reflect your x's, you actually reflect it across the y-axis. So there's one type of transformation we'll see, and we'll see two others. We're going to see dilations and also translations. So next up is a translation. A translate is when you shift. The rules will apply that if something's on the outside of the equation, it'll translate the y's, it'll add or subtract on the y's. If something's on the inside, adding or subtracting, you'll actually add or subtract on the x-axis. X's will always lie. Okay, and finally, last rule, and then we're going to actually start math. Vertical and horizontal dilations. This is when you stretch or shrink a graph. If it's on the outside, it'll multiply or divide the y values. If it's on the inside, it'll do the same with the x. But inside is a liar. You're going to hear me say a lot. That x's lie, y's tell the truth. I will play off that and I'll say that's why we dumped our x's. Our x's were always lying to us, and that's why we married our y. Because our y was telling us the truth. You're going to hear me say it until you think it's so dumb and so cheesy, but I don't care. I'm going to keep on saying it because I want to make sure you get it right. So that's what you're going to hear me say. And that's what this is explaining here. With all that, let's get started. Example 1, it says use the function f of x equals x cubed to graph and describe the transformations that have occurred if g of x equals negative f of x minus 1 minus 4. Okay, so first thing I want you to do, without cheating and going back, do you remember what the shape is of x cubed? I'm going to do a countdown here. Do you remember what x cubed should look like? 5, 4, 3, 2, 1.
S curves.
All right, put that up top here. S curve. I know I don't ask for it, but it's helpful if you know what they look like. That's the parent function. Now we're going to transform it somehow. There's going to be 3 transformations here. Before I get to that, let's fill in this table here. If I plug in these x's, let's see. What is negative 2 cubed? I'm just plugging it into the equation here. So the y is equal to the f of x. So let's plug in negative 2. What's negative 2 times negative 2 times negative 2?
Negative 8.
Negative 2 times negative 2 is a positive 4 times by negative 2 is a negative 8. I agree. I'll do this in black. That will be negative 8. Okay, what about negative 1 cubed? What's negative 1 times negative 1 times negative 1?
Negative.
3 negatives make a negative. Negative times, or 1 times 1 times 1 is 1. I agree. Okay, what about 0 cubed? 0 times 0 times 0 times 0.
0.
All right, great. What about 1 cubed? 1 times 1 times 1 times 1. 2 times 2 times 2.
8.
And 3 times 3 times 3. 27. Great. Now I'm going to graph this, and we'll call this f here. The graph, the only points I can really plot are at 0, 0, 1, 1, negative 1, 1. And after that, I start going off the graph. So 2, 8 would be somewhere up here. So if you want to graph this as best you can, this S curve, whoops, I'm already missing. This is terrible. I don't even know what I'm doing. About to just have to give up. All right, let me try one more time. This would come up like this. And then over here, your S curve would go down the other way. Need to be up by my board. It's a lot easier if I can actually see what I'm drawing on. Okay, that's super ugly. But that might be the best I ever get. Believe it or not, my wife is an artist. I have 0 art skills though. Now let's talk about the transformations. Here's how we do transformation. Oh, by the way, what's the domain here?
Negative, no, positive.
So one of the questions you could ask yourself is, if you refer back to the poster, do you see any divisions in this equation? In x cubed, do I have any divisions? Do I have any logarithms? Do I have any square roots? No, so it's going to be all reals. You could say negative infinity to positive infinity, or you could say XER. Now, what about the range? How low, how high?
Negative.
Negative infinity to positive infinity. It's why all reals. Okay, so now we're going to go into G. And we're going to do its transformation. So I want you to look at G's equation here and tell me what's happened. Now, I start on the inside. This is where transformations of x occur. Now, it says to -1, but that's going to be a liar. What is the opposite of subtracting 1?
Plus.
So every x value is going to get added by 1. So right now, my x values are -2, -1, 0, 1, 2, 3. I just add 1 to each of them. So -2 plus 1 becomes -1. So it's going to go -1, 0, 1, 2, 3, and 4. Okay. So all I do for my x's is I add 1. X plus 1. Now for my y's, this says take a negative. F represents the y. So it's a negative y. And then -4 more. So I go to my y column. You're going to take a negative of the y and then subtract 4 more. So it's negative of -8.
8.
So negative of -8. And then you're going to subtract 4 more. What is a negative of a -8?
Positive.
8 minus 4?
4.
4. That'll be the first value. So now we'll do it again. Take this -1. What's a negative of a -1?
1.
1. Subtract 4 more.
Negative.
Negative of -1 is 1. Subtract 4.
Negative 3.
-3 is what it's going to be. Okay. 0. What's negative of 0? Still 0. Subtract 4. Okay. Here, I take my 1. What's negative of 1? Subtract 4 more. Okay. 8. Take -8. Subtract 4 more.
4.
I'm getting -12. And then 27. -27 minus 4 more. Okay, so let's plot the ones that we can fit on this graph here. -1, 4, I can plot that. -1, 4, 0, -3. One, -4. And 2, -5. Those are the only ones I can fit in this graph. So this is my S curve coming through this way. My S curve coming around this way. Like that. And that would be G. This was F. Okay, so let's just describe these transformations. This negative right here. Oh, let me do domain range. The domain range. You can do the math off of this. All it says is to add 1. So what's negative infinity plus 1? It's still negative infinity. So I'm going to just do the math. What's positive infinity? Add 1 more. Still positive infinity. So it'll be all reals. Infinity is the only thing that can ever happen though is change from negative to positive. That's the only thing that can ever change with the infinity if you have that mathematically. Okay, so over here, the range. You would make it negative and then subtract 4. So what's a negative of a negative infinity minus 4? That'll become a positive infinity. So this negative infinity, when you do this transformation, is going to become a positive infinity. And then this positive infinity, if you plug that in, becomes a negative infinity minus 4 more. Which is a negative infinity. So these stay all reals. This does not change. You can look at the picture and it goes left and right both ways forever. Okay, I'm going to describe the transformations. This right here, a negative, if it's just a negative, It's a reflection. If you're reflecting the y values, that's on the outside, which axis do you cross?
X.
Okay, we have a reflection across the y-axis. Go ahead and add that in your notes if you can. Okay, what about this transformation here? Did we actually subtract one? We added one. If you add or subtract a number, that's a translation. This translates 1 unit. Which way does it go? If it's with x and it's a liar. So here's your x-axis. Instead of subtracting 1, you add 1. Which way did it translate it? It went right because it's a liar. It went to +1. And then out here, this -4, this again is a translation. Anytime you add or subtract, it's a translation. Translates 4 units down because y is a truth teller. So that's how the graph has been shifted. Ruby, still there? Okay, so spent a lot of time there walking you through that. I'm gonna try to pick it up, but we're gonna do this 2 more times. Yep, I'm gonna do it 2 more times before I'm gonna ask you to do it. So I know this just says example 1A. This really is tying together all the different ways you might see it. You might see it in equation form. You might see it as a table. You might see it as domain and range. You might see it as a graph. But that's how the transformations work. One more thing I want to add to this. Just to pick any one point, if I took the point -1, 1, I could show that this -1, 1 corresponds to 0, -3. This point right here became that point right there. This point here transformed to become that point there. And 1, 1 became 2, -5. That's how the graph was transformed. All those along the way. That's where the pieces move. Those are the corresponding pieces. If you go down, that was -1, 1, 0, 0, 1, 1, becoming 0, -3, 1, -4, 2, -5. Okay. Now let's do this again. First question I have for you on this one. It says the parent function is the square root of x. What did that look like as a shape? Do you remember? Square root of x. Half a sideways parabola. And by equation, you could also see this as x to the 1/2. All right, let's get our table to begin with. What is the square root of -2? You can't take a square root of negative. Look up there on the whiteboard. Domain rules. What does it say about it's rule number 2? You can't take the square root of a negative number. So these two right here are going to be undefined. You cannot take the square root of -2, nor can you take the square root of -1. These are undefined. These are imaginary numbers. But starting at 0, I can take a square root. What's the square root of 0?
0.
What's the square root of 1?
1.
What's the square root of 4? What's the square root of 9? And the square root of 16? 4. Okay, so as we look at the domain and range, this is not all reals because I have some undefined. Where did the domain begin from?
0.
0. And that gave us a real number. That is a real number at 0. So I want to do a bracket. It's equal to a real number from 0. And how long could I keep doing square roots? Infinity. It'll be 0 to infinity. Or you could do x is greater than or equal to 0 as well. And now let's take a look at a range. What was the smallest value of the range? 0. And how large will our range get? Infinity. It'll continue to rise. You could say y is greater than or equal to 0. Okay, so this is going to be the table for f. If we wanted to plot this, go to 0, 0, 1, 1, 4, 2, and now we'll be off the graph. There's your graph of f. Okay, so now let's talk about this table over here. Tell me what's changed with the x's on the inside. What's happening with my x's? Yeah, why are we subtracting 4? Because the inside lies. So every x value gets subtracted by 4. So -2 becomes -6, -1 becomes 0 becomes 1 becomes 4 becomes 9 and 16, 12. Good. Now let's talk about our g's. I mean, yeah, our y values. Sorry, our y values. What am I doing to y? I'm multiplying by 3. So 3y minus 2. So what happens when you try to multiply undefined by 3 and then subtract 2? Still undefined. So we have undefined here, undefined there. So undefined and infinities don't change. The only thing that can change with infinities are undefines. Or rather, the only thing that can change with infinities is that it can become a negative infinity from a positive or vice versa. But other than that, they don't just all of a sudden become a number. Okay, now let's start plugging in. 3 times 0. What's 3 times 0? Just a reminder what I'm doing here. I'm plugging into this y value. 3 times 0 minus 2. What is 3 times 0 minus 2? -2. Okay, so here I'm plugging in 1. What's 3 times 1? 3 minus 2? 1. Okay, great. Now we plug in the 2. What's 3 times 2? Subtract 2. 4. 3 times 3? Minus 2. And finally, 3 times 4? Minus 2. And there's our table there. So we plot these. The only values I can get is -4, -2, -3, 1, 0, 4, and 5, 7 will be off the graph. 5, 7 would be somewhere up here. I don't know. So graph should look something like that. Okay, so just to list where our values got transformed from one location to another, we could say that this point right here became this one. These two correspond. These two correspond. These two correspond. That's how the graph's being transformed. This just an arrow one in. I'm gonna try something. Yeah, there we go. I want to use these arrows. So try it one more time. So you can see where it's going from where to where. Like that. Okay, just to write up these transformations. This is multiplying by 3. Whenever you multiply, that's a dilation. When you multiply the y's, you call it a vertical. This is a vertical dilation. That means you're multiplying by factor 3. Okay, what about in here? What happens when you add or subtract a number?
It goes left to right.
It'll translate. This is a translation. Translation which way? If it's x plus 4.
Right.
Left, because it's a liar. Translation 4 units left. And then finally, what about here? A -2 on the outside. Anytime you add or subtract, it's a translation. And that's a true teller. It's on the outside. So it's translation 2 units down. There you go. All right, I'm gonna do one more time. See if we can get a hand cramp. And then I'll let you try one. What can you tell me about the shape of this equation here? It's a V. This is V-shaped. Absolute value. So it's V-shaped. So what happens when you take the absolute value of -2? +2. What about the absolute value of 1? -1. Absolute value 0. 0. Absolute value 1. Absolute value 2. So we should get a V that goes through these points. So if we start plotting our points, -1, 1, +1, 1, -2, 2, +2, 2. Those are the only ones I put on there. We would have, you could do more points. This time, rather than me draw bad lines, I'm going to use my tool. So it would look like that. There's your V, Kevin. Kevin. Okay, what can you tell me about the domain? Do you see any division in the equation? Any logarithms? Any square roots? Anything like that? In this equation, do you see any of that? No, so it's going to be all reals. Notice there's no breaks. It goes forever left, forever right. So our domain is all reals. Negative infinity to positive infinity. Negative infinity to positive infinity. Or you could say X, E, R. It's all reals. What about the range? Does this graph look like it's all reals? Very good. You go bottom to top. So Evelyn said to do which one first? What did y'all hear what she said? You go bottom to top. What's the lowest value here? 0. And again, it hits it. It doesn't just go there. It actually gets there. So it's a bracket. And then how high? Infinity. Now you don't ever get there. So it's a parenthesis. This is, you could rewrite this as y is greater than or equal to 0. Now let's take a look at this transformation here. So what's happening on the inside? It says that x is being subtracted by 3. It says x is being divided by 2. When you look at the inside, you got to start with the outside thing first. What's it doing? Dividing. So, because technically it's dividing everything. That's why I'm going to deal with this. So what is the lie of division by 2? Multiply. This is actually going to double our x value. We will first double the x, and then what's the lie of -3?
+3.
Plus 3. Now, I had a student ask before, well, wait a minute. Doesn't this get to, and it's true, this technically you could rewrite this like this. But here's the reason why math lies, the x's lie, I'm sorry. It's because you would set it equal to 0 if you were solving. What would you do first? You would add 3 halves. So right now you're like, well, why isn't this 3 halves? Why is it a 3? Well, after I add the 3 halves, I have x over 2 equals 3 halves. How do I get rid of a division by 2? Multiply by 2. Well, when I multiply both sides by 2, it cancels on both sides. And what are you left with?
3 and x.
A 3. And so that's why it's a 2x plus 3. Okay, so that's how that works. I'm going to erase this so you're not confused. But that, because this division's covering everything, you would do this first. So you double x, then you would add 3. And what's going to happen on my y's this time? All I have is a +1, so it'll just be +1. Y plus 1. That's a liar? I mean, or a truth teller? Is that a liar or a truth teller? That's a truth teller. Okay. So now what we're going to do is we're going to double our x values, then add 3. So double the x value. I put in -3, I'm sorry. Double the x value, then add 3. What is 2 times -2? +3? -1. Okay, next one. Sorry, there you go. The next one, we're going to multiply 2 times -1, then add 3. What's 2 times -1? -2, add 3. 1. What about 2 times 0? 0 plus 3. 2 times 1. 2, add 3. And then 2 times 2. Add 3. So those are our x's. Let's find our y's. We just need to add 1. So instead of a 2, it becomes 3. Instead of a 1, it becomes, instead of a 0, instead of 1, instead of a 2, 3. Now we plot these points. So we have a -1, 3. a 1, 2, a 3, 1, and a 5, 2, and then I'm cut off screen after that. So I'll add those in. So that would be my graph of G. Now, is this domain still all reals? Yes, because they're dealing with infinity. So even if you double them, then add by 3, it's still all reals. So the domain does not change. Negative infinity to positive infinity. XER. Now the range changed though. It says add 1. So instead of it being a 0, what does it become now? And instead of infinity, well, what's infinity plus 1? Still infinity. So that one actually doesn't change. Infinities do not change unless they switch from positive to negative. You could rewrite this as y is greater than or equal to 1. Okay, there's a lot going on in the transformations. This 2 right here. What do we actually do to the x's? So this is a horizontal. Anytime you multiply or divide, it's a dilation. Horizontal dilation. What we actually did is multiply by 2. So you'd say by factor 2. It was a horizontal dilation by factor 2. What about up here, this minus 3? What did that actually do?
No, to the right.
Translation, which way, left or right?
Right.
We added, so it was a translation 3 units right. And finally, the plus 1 on the outside. Anytime you add or subtract is a translation, which way to go?
Up.
1 unit up. Okay, you've seen me now do this a number of times. I'm going to give you a DOL to try. Oh, am I wrong? I didn't realize we had x squared. Okay, sorry. I forgot I did a part D. We'll run through this one quicker. What's x squared going to look like? Let's shape. We should get a parabola. The domain, you could go ahead and fill this in. There is no squared. I mean, there's no divisions. There's no square roots. There's no logs. So the domain will be all reals, negative infinity to positive infinity. This is all reals. If we wanted to plug in our numbers to get the range, what is negative 2 squared? Negative 2 times negative 2. 4. What is negative 1 times negative 1? 0 times 0. 1 times 1. 2 times 2. 3 times 3. There we go. If we wanted to plot these, we'll have a point there. 1, negative 1, 1, positive 1, 2, negative, excuse me, negative 2, 4, and 2, 4. We had all those points. You can connect those for your parabola. Whoops. So is the range all reals? No. How low? Sorry, how low does that go? 0. And I'm going to do a bracket because it's actually getting to that point. It's not heading there. It actually gets there. How high? So you could say y is greater than or equal to 0. All right, let's now talk through the transformations. I have this negative 2 out front. Is that going to be changing the x's or y's? Transforming x's or y's? Y's. Is that a lie or truth teller? Y's tell you the truth. So we're going to multiply those by negative 2. And now on the x's, a fraction works like this. It's saying to multiply by 3, divide by 2. Multiply by 3, divide by 2. Now, is that a liar or truth teller? a liar. So what we're actually going to do is instead of multiply by 3, divide by 2, we're going to multiply by 2, divide by 3. Notice you just take the reciprocal if it's a fraction on x. Do the reciprocal. So this gets to be pretty crummy here. -2 times -2. I'm sorry, -2 times 2 is -4, and then you would divide it by 3. It won't reduce though. 2 times -1 divide by 3. 0 times 2/3. 1 times 2/3. 2 times 2/3. 4/3. And finally, the one good number I give you, 2/3 times 3. 2 times 3 is 6. Divide by 3. 2. It's the only good number we get there. Over here, what is 4 times -2? -2 times 4. -8. 1 times -2. 0 times -2. 1 times -2. 4 times -2. And then 9 times -2. Okay, so let's plot those points. We have 0, 0 again. And then it's the next one I can fit on is -2/3, -2. So somewhere in here, somewhere in there, +2/3 and -2. And that's it. So it goes something like that. Not a very pretty graph. Okay. Domain, is it still all reals? Yes, if you start with infinities, it's going to stay with infinities. You can't change infinities other than positives and negatives. That's the only thing. What about the range? Is it still 0 to infinity?
Yes.
Yeah, because when you multiply by -2, the 0, what's 0 times -2? 0. So I still have a 0, but when I do -2 times positive infinity, it becomes negative infinity. So negative infinity is smaller, it goes first, and 0 becomes my larger number. So now we'd say y is less than or equal to 0. Just to make sure you understand where the points went from one place to another, the origin did not move. This one went down here, and that one to there, and so on. Let's write what the transformations, what happened here. A negative is a reflection. This is reflected. If you're reflecting your y's, which axis across? Now, not only are we reflecting by our y's, we are also multiplying by 2. Whenever you multiply, it's vertical if it's y. What do you call it when you multiply or divide by a number? Starts with a D. Dilation. They'll call that a dilation. By factor, and you put whatever you multiplied by. By factor, 2. Now, what about this one here? The 3/2. That's on the inside, so it's not vertical anymore. Now it's horizontal because it is multiplying. It's still a dilation. By factor. Now, did we actually multiply by 3/2? What did we multiply by instead? By factor of 2/3. Now, I have a DOL for you. Here's what I want you to do. The table is really tricky. I want you to graph this based off of what it should look like. If you need to flip back, go ahead, and then do the transformations on the graph. And then, well, no, the table's not that tricky to plug in. I don't know why I'm saying that. Yeah, go ahead and find that. But when you get into the graph, don't graph by points because they're all going to be weird fractions. I would just graph based off of what you know the parent function should look like. You can look back to see what it should look like, and then transform it by what it says to do to get your values. But I'll give you some moments to try to do this now. All right, let's take a look now at example 2. It says identify the parent function for the graph f of x and then write an equation g of x for the shown transformation. Okay, what type of equation creates a v graph like this? That is I heard one answer. What makes a v my v shape like this? Absolute value. So the parent function it asks for first, put that right here. This is the absolute value of x. Now I'm going to write down a couple points. It says to use this one, but if you only use one point, it's hard to tell all the values. So I'm also going to use this vertex point. This vertex point is 0, 0. And I'm going to include this point as well. So I'm just, whenever you do it from a graph, I would recommend taking at least 2 points. So I'm just going to do 2 points. What is that point right there? 4, 4. 4, 4. So we're going to add that to our t-chart. Now let's look at the corresponding piece. The vertex is still 0, 0. That has not changed. 0, 0. So that was that point 0, 0. That has not changed. But 4, 4 has changed. What is it now? 1. I hear 1, 4. That's not accurate though. 1, negative 4. 1, negative 4. Okay. So now you can look at it and figure out what's happened. Have I just subtracted 3? You see how 4 minus 3 is this one? Did I actually subtract 3 on my x's?
Yes.
It looks like on the second point, but it's not accurate. Why is it not subtracting by 3? Because what would be 0 minus 3? Would it still be 0? No. So I got to think of a different way. How can I make 4 become a 1 without changing the 0? Divide by 4. What we actually do here is we're dividing our x by 4. Very good. 0 divided by 4 is still 0. 4 divided by 4 is 1. Okay, now let's look at the y's. A 0 remains a 0, but a 4 becomes a negative 4. How do we make that happen?
Multiply by negative 1.
You multiply by negative 1. So you could just say negative y. So what does that mean our equation is? Well, you would say this way. You'd put the negative out front. So it would be negative f of, and on the inside with x, if it says to divide by 4, what does that mean by equation I need to do? So I want to say 4x in parentheses. You could write it that way, or if you wanted to go to the parent function here, oh wait, we didn't write that. There it is. If you want to do it from there, you could say negative on the absolute outside of the absolute value with 4x being on the inside of the absolute value. You could do it that way as well. You could write it either way. Both of those would represent the same thing. I just want to show you how the table works. What's the domain for this absolute value? All real numbers. What was the range for the original parent function? 0 to infinity. Okay, now let's look at the transform graph. When you divide infinities by 4, what happens when you divide those by 4? Did dividing by 4 change infinities? No, they're still infinities. So it's still negative infinity to positive infinity. Okay, but the y's become negative. So instead of being 0 to positive infinity, okay, but we have to go from smallest to largest. So I wouldn't say 0 to negative infinity. I would now say negative infinity to 0, like that. So now y is less than or equal to 0, whereas over here y was greater than or equal to 0. Okay, go ahead. All right. Let me give you this one here. Let's see what's happened this time. These look like C curves to me. What's the parent function of a C curve? It's 1 over x, which you could also write as x to the negative 1 power. Okay, let's write down some points. What's this point here? 1, 1. Whoops. 1, 1. And what's this point there? Negative 1, negative 1. So we're going to put those on our table. So negative 1, and 1, positive 1. Now, what about on G? This 1, 1 point becomes
3, 1.
3, 1, and this point becomes so -3, -1, and 3, 1. Okay, so what happens to get from x to x? We're multiplying by 3. It's 3x, okay? And what happens on the y's? Basically nothing. So what does that mean my equation is? Well, you could write it this way. If it would just be f of, you don't do anything to the y's. If I actually multiply by 3, what would it look like in the equation?
3x.
X divided by
3.
3. Now that's in function notation. Now, as I plug it into this equation, here's what's weird. It says 1 over x, but you're supposed to divide this x by 3. Do you know what happens if you divide the denominator? It's multiplication of the numerator. Very good. I'm going to write that out. If you take 1 over x, but that x itself is supposed to be divided by 3 like that, that is the same thing as 3 over x, putting the 3 all the way to the numerator. So you could write it as 3 over x, or you could put f of x over 3. Domain range. What could we not equal here as far as x goes? 0. X could not equal 0, but x can equal all other real numbers. When you multiply that by 3, what's 0 times 3? Still 0. So the domain doesn't change. Because all we did was multiply by 3. The range. Looks like the range is that y doesn't equal 0. And we don't change the range, so it stays y does not equal 0. All right, with that, we come to your second DOL. All right, let's conclude by looking at example 3 here. So if it says the function f has domain from -3 to 4 and a range of -4 to 1, the function g is given by this transformation. What are the domain and range of g? So let's just think through what would happen here. From going from function f to function g, what I'm going to do here is kind of the way we were with our table, is by table we would say the x is being changed here. Oh man, this looks kind of weird. If you said 2 minus x equals 0, I would subtract 2 first. So it looks like negative x would equal -2. So it looks like I would subtract 2, but I have this reflection here. So when I reflect, it actually is going to make the -2 become positive. So what I'm actually going to do is I will add 2, but I'm going to have to flip my x's. And then for the y on the outside, I'm multiplying by 4. And I should have said these are the y's. This is the truth. Okay, I'm going to multiply by 4. And then I'm going to subtract 1. 4y minus 1. So why am I doing that? Well, they gave me the domain and range, which is kind of like the x's. So for the value -3, when I multiply that, or the first thing I do is I make it negative. So -3 made negative is +3. Then I'm going to add 2. So right now it would look like this, 5. So negative of -3 is 3. Add 2 is a 5. And then the 4, I make it negative, -4. Then I add 2. So 4, -4, add 2, -2. Now, as I look at this, this isn't in the right order anymore because I'm going larger number to smaller number. So I need to flip this around. I'm going to correct that first. We'll say the domain is going to be from -2 to 5. And now I come over here. The range, it was -4 to 1. I need to multiply by 4, then subtract 1. -4 times 4 is going to be a -16. Subtract 1 more, -17. This was a bracket. And then the y, value of 1. 4 times 1 is 4. Subtract 1, I get 3. This again was a bracket. And so my domain, so we don't, this is out of order. Out of order, and so that's why I'm crossing that out. And so the domain of G, so G's domain would be -2 to 5. Whoops, not parentheses, sorry, bracket. And the range would be -17 to 3. Okay, let's reload and try this again. Okay. This time, the domain, let me do the original here. Do it like this. The original is all reals, -infinity to +infinity. And the range is -2 to infinity. And now let's do the transformation over here. Let's see, it says 2 times x, so x is a liar. So I'm going to take my x and divide it by 2. And then for the y, so I'm going to have -3 times y plus 5. So to break it down, I would have -infinity divided by 2 and infinity divided by 2. And over here, maybe I should have been doing this the whole time. I think it might be easier this way. -2, whoops, excuse me, -3 times -2 plus 5. And then it'll be -3 times infinity plus 5. And that one's a parenthesis. So if I simplify, infinity divided by 2 is still infinite number. So we're just going to say this is still all reals for -infinity to +infinity. However, on the range, -3 times -2 is a +6. Add 5 is 11. And over here, -3 times infinity becomes a -infinity. When you add 5, it's still -infinity. Now this is out of order as well. Out. Oops. Out of order. So I would need to rewrite that as -infinity to 11 this way. And for the record, you could say y is less than or equal to 11. And over here, you could say x is all reals. But those would be our answers. That's how we do that. So you could say it this way. There's your domain. And over here, this would be the range. And now here's one for you to try.